I am very happy to present a new idea for a space telescope that can discover all habitable exoplanets within 10 parsecs of the Sun. 10 parsecs is the distance light travels in 33 years. The telescope is then capable of discovering oxygen in the form of ozone in the atmospheres of those exoplanets. I'd like to thank my collaborators pictured here, and in particular, I'd like to thank my graduate student, Leif Sordi, who did all of the ray tracing, CAD drawings, figures, and calculations upon which this talk is based. Habitable planets are those that have a temperature that supports liquid water. We're used to seeing planets in reflected visible sunlight as they're pictured here. The yellow spectrum on the left shows sunlight as it is reflected from the surface of the Earth. The emission spectrum, which is shown here, the blue background, peaks at 10 microns. Habitable planets are easier to see in their infrared emission spectrum because the Sun and large outer planets have much lower emission at these wavelengths. At 10 microns, the Sun is only 1,000,000 times brighter than the Earth. Light takes 33 years to travel 10 parsecs. Within this local volume, we aim to find all of the habitable exoplanets that we could imagine communicating with or launching a probe to investigate, and that we have the best chance to study with a future NASA-grade observatory such as the Habitable Worlds Observatory. Our concept is called the Diffractive Interferocoronagraph Exoplanet Resolver, also known as DICER. To see the Earth around the Sun in 10 micron wavelength light at a distance of 10 parsecs requires the diffraction limit of a 21-meter space telescope. Our new design reaches that diffraction limit using two 10-meter flat diffraction gratings and two 1-meter square infrared telescopes. This is small enough that we can imagine fitting it inside a currently available launch vehicle such as a Falcon Heavy. On the lower right, I show just the optical elements of DICER folded up next to the Falcon Heavy. Maybe we're not quite there, but we're pretty close. DICER collects light with a diffraction grating, which gives us the large dimension required to resolve an exoplanet from its host star. The light is focused with an infrared telescope. In order to see the whole grating, this telescope must be mounted at a large angle of exodus from the grating. As we increase the angle of diffraction, the light collected in the field of view of the secondary telescope becomes redder and the bandwidth narrows. To see the whole grating, the focusing optics must be mounted almost at grazing angle. This large diffraction angle produces a large wavelength dispersion and therefore a very small wavelength range that is collected with the secondary telescope. Although the total amount of light collected depends primarily on the diameter of the secondary telescope, the angular resolution is determined by the length of the primary grating. Our benchmark design uses gratings that are 10 meters long by 1 meter wide with a grating pitch of 10.055 microns. The light is focused with a 1 meter by 1 meter square Ritchie-Chrétien telescope with a field of view of 0.8 degrees. The wavelength range of the light collected is only 14.7 nanometers wide, centered at 10 microns. By putting the light from two gratings together, we use interferometry to eliminate the light from the host star. The two gratings are pointed directly at the exoplanet host star so that its light comes in exactly perpendicular to the grating. Since the diffracted light is collected on opposite sides of the two gratings, the spectrum of the host star and exoplanet are initially reversed. Then, light from one of the gratings is pupil inverted. In our case, we do this with periscope optics, which are pictured on the lower left-hand side of the slide. This lines up the spectra from each side so that the wavelengths of the light from the host star are exactly aligned and out of phase, thus nulling the light in the combined focal plane. Since the light from the exoplanet is on opposite sides of normal for the two gratings, it is imaged in different parts of the focal plane, and as long as it is resolved from the host star, it isn't nulled. In our FRED ray trace of the system, the host star is nulled by a factor of 10 to the 14th, which is the limiting precision of the program. However, stellar leakage from a star the size of the Sun at a distance of 10 parsecs limits the reduction in light from the host star to a factor of 2 million. A pointing jitter of 1 milliarcsecond, which is the pointing jitter of JWST, limits the nulling to a factor of 100,000. Better pointing control, or wavefront sensing, could in principle improve this, but for our proof of concept design, we assumed that the pointing jitter would be the same as JWST with no additional correction. This makes the leaked light from the host star 10 times as bright as the exoplanet. I'd like to draw your attention to the combined focal plane, which is circled with the red ellipse on the bottom right of this slide. When we started designing DICER, we thought we could just add up all of the light from the star and from the exoplanet that landed in the combined focal plane of the coronagraph in order to detect the exoplanet. The wavelength range of the light that's collected there is only 14.7 nanometers wide. And while in principle the R equals a million resolvents of the grating would allow very high resolution spectroscopy, there are very few photons populating that spectrum, and the rotational bands that we're trying to look at in the infrared are much wider than our bandwidth, so adding all the light together seemed like a good idea. However, this doesn't take into account that the diffraction grating will transmit light from objects all over the sky. Here I show light from the host star hitting the gratings as a plane wave and being collected by the secondary telescopes. But if the light from a star comes in with a positive angle of incidence, the secondary telescopes will receive light with a longer wavelength, and if the angle of incidence is negative, then shorter wavelengths will be collected in the focal plane. In fact, we collect some light from stars located in an area 100 degrees across in the long direction of the grating. This slide just shows that the angles of incidence are reversed for the other grating, but we still collect light of varying wavelength across the sky. We can cut out most of these objects by placing a filter of width 14.7 nanometers, which is our detectable bandwidth in the beam. While this cuts out most of the unwanted light from other objects in the sky, it still lets through a zodiacal light background from an area that is 100 arcseconds in the diffraction direction of the grating, by 1 arcsecond, which is the resolution of the point spread function in the short direction of the grating. To reduce this unacceptable background level, we need a second disperser. This second disperser will disambiguate direction in the sky from wavelength collected. I show here a Fred ray trace of the coronagraph using 3 wavelengths of light going to a curved focal plane. Since the primary objective gratings have R equals a million, we would be able to achieve the full resolution of the grating, 1 arcsecond by 0.1 arcsecond, if we had a second spectrograph with R equals a million. However, at this time we only know how to make a spectrograph with R equals 100,000 using an immersion grating design copied directly from the canceled Spica satellite. Here we show the location of 5 Spica-style spectrographs in relation to the DICER observatory. This CAD drawing shows 5 immersion grating spectrographs covering the focal plane of the coronagraph. The small circles show the position of the focal plane. The light goes through focus, then into the immersion gratings. The light comes back out and is picked off by the small circular mirrors and is ultimately focused on the set of 5 square green detectors in the back. The left panel of this slide shows DICER pointed directly at the host star. The middle panel shows the exoplanet transmission as a function of the rotation angle of DICER, and the right panel shows the transmission as a function of angle in the sky. The blue band in the middle is where the coronagraph nulls the light. To discover an exoplanet, the observatory is rotated while staring at the star. When the exoplanet is aligned with the long axis of the grating, we resolve the exoplanet from the host star, and a signal of roughly half the theoretical photon rate from the exoplanet is detected. When the exoplanet is aligned with the short direction of the grating, it is not resolved from the star and is therefore nulled, giving us no signal. The modulated light from the exoplanet depends on its position angle and distance from the star, and therefore can measure both of those quantities. There are of order 70 Sun-like stars within 10 parsecs, and these can be scanned for exoplanets one by one, rotating the observatory while staring at the star to detect the modulation that tells us a habitable exoplanet is present. By taking repeat observations, we can trace the orbits of the exoplanets and find exoplanets that are in front of or behind the host star during some portions of their orbit. Once an exoplanet has been detected, we can search for the ozone absorption band at 9.6 microns. Tilting the gratings by 5 degrees will change the wavelength of light detected by the system from 9.3 microns to 10.2 microns, spanning the ozone absorption band. This animation shows that tilting the gratings changes the wavelength of the light detected. We can measure the luminosity on each side of and in the center of the ozone band. A low reading in the center compared to the edges indicates the presence of ozone. I've presented a benchmark optical design for DICER, an infrared space observatory that could plausibly detect all habitable exoplanets within 10 parsecs of the Sun, or show that they don't exist. DICER will measure orbital parameters and possibly a surface temperature for each exoplanet, but it will also detect or rule out ozone in the atmospheres of those planets. The detection of ozone in the atmosphere of a habitable planet orbiting a sun-like star would be a strong indicator that photosynthesis is happening on that planet. And if such a planet were discovered, one could imagine launching a probe to go find out more about that candidate Earth 2.0.